bond theory there to draw the orbitals and everything for that. Well, what if maybe, what if we just redraw it like this? Kind of just put it into an orientation that maybe you're a little bit more familiar with. Because remember how we did ethene? And it was like on the side like that? So I'm kind of trying to get you to look at it from that perspective, something that you're familiar with. Now, what is the hybridization state of that carbon right there? sp2. And so the carbon is going to have the sp2 hybridized orbitals right here and our p orbital. That looks like that, correct? Now, what is the hybridization state of that oxygen atom? sp2 as well. But isn't there only one electron group around there? No, there's 3 of them, right? Because we have some lone pairs there. So that oxygen is sp3. If the formal charges are shown, then I don't need to tell you how many lone pairs there are. Okay? Because you guys are going to know how, oh, that oxygen atom is neutral. It has 2 bonds, so I know it has 2 lone pairs. You're going to get to that point if you're not already. Okay, I don't need to draw in lone pairs all the time. So that is sp2 as well. So what does the ground state of oxygen look like? Well, we see that it's in what? Group 16, so it has 6 valence electrons. So in the ground state, we have 2s and 2p, 6 valence electrons. That looks like that. But you just told me that that oxygen is sp2 hybridized. So we have to draw those hybridized orbitals. There's our sp2, there's our p. How many valence electrons does oxygen have? 6, so we just put those in. Okay? So there's our electron configuration that we are going to use now to draw our formaldehyde. So we have our carbon atom, and we said that it has what? It's sp2 hybridized, so it has a orbital there and there, right? And then it also has what? A p orbital. And we can account for those electrons. So we have 1, 2, 3, which is account for those. And then we have 1 in the p, just like that. We then also have what? The oxygen atom. And we said oxygen atom is sp2 as well. Let's move that over a little bit. Okay. So that has sp2, sp2, sp2. It also has a p orbital. So where do those electrons go? So what we have here in that area right there, that is what? A sigma bond, right? So we need to have something that has an electron that can form that sigma bond. Would it be this orbital right there? No, that's in a p. We're saying that this orbital right there is sp2, so it has to be this guy. So it's that electron that's going to go in there to form that covalent bond. So if we go like this, we've just described that sigma bond. We also can describe a hydrogen coming in and another hydrogen coming in right there to describe those 2 bonds. And we've seen that like 4 times now, right, with all the examples. So where's this electron? Where are these guys? Well, my diagram tells you where they're at. They're in sp2 hybridized orbitals. So those lone pairs, so when we look at oxygen here, those lone pairs right there are in the sp2 hybridized orbitals. So you're going to see questions like, you'll see this molecule and I'll point to a lone pair and be like, what orbitals are they in? And you'll be able to answer that. Just draw the configuration that I'm doing here. And then we account for that electron there. And now we have the pi bond above and below that plane, which is going to account for that bond right there. And I think I have that exact same problem on my YouTube channel, but I don't remember for sure. But you see the process? It's the same thing that we've been doing last time. It's just now with an oxygen atom. You just do the same process. Find the hybridization state. Find how many valence electrons there are and just fill it in. But this one is a little bit more tricky because you have to use some chemical intuition and figure out, okay, which one of these electrons right here is going to be responsible for the sigma, which one's going to be for the pi. All right. Any questions about that problem? Feeling good about that? That if I gave you a molecule you've never seen before, you could use valence bond theory to draw all those orbitals?